little introduction.
You want to say something?
So we have saved the best for last. This is all from Dreele, as you already know. We're really proud to have him here, and he has an amazing career in X-ray diffraction, worth of 10 lifetimes of regular person. I don't think there's introduction that's going to make step up to the size, so I just let him speak. Thank you, Bob, for being here.
Okay, thank you. I always enjoy coming to Canada because the thing that's on sports news is ice hockey. Okay, I'm going to talk about the Rietveld method in some detail, talk a bit about least squares, the actual how least squares really works. But the thing I want to start with is the logo for GSAS-II is a real molecule. Does anybody recognize it? There's got an awful lot of oxygen in it, and there's some nitrogens in it. It is pentaerythryl tetranitrate, which is something that I did as a high-pressure experiment, and it is a high explosive, otherwise known as PETN. And it's a really cool-looking molecule. Anyway, so I'm going to be talking about, and I should also point out that I am retired from Argonne National Laboratory, which doesn't mean much because I'm still working for them. Okay, let's see if we can get to the next one. Well, as Joel pointed out, the Rietveld refinement was created in the late 60s, and it is basically a curve-fitting process. You know, you have a collection of points and you fit a straight line to it. Well, it's the same mechanism as that, except that the curve is not a straight line. It's a very complicated powder pattern. And so what that means is that each point in the powder pattern is modeled by a collection of peaks underneath it, each one making a contribution to the point in the profile. And so the modeling of it consists of representing the calculated curves that goes through these points, the observed data set. There was a lot of controversy about the Rietveld method back in the sort of 1980s because people got hung up on the idea, well, how many reflections are in your data? There's none. If you think about it, there's no observed reflections in a powder diffraction pattern. The observation is points in the pattern. The peaks are part of the model. Just remember that. The reflections are part of the model that's used to fit the powder diffraction pattern. Okay, so the kinds of things that are used are the same sort of description for the residuals that one uses in single crystal crystallography, except you have powder intensities rather than the single crystal structure factors. But the R value is defined pretty much the same way. You minimize the same sort of function, which is the weighted differences between the observed and the calculated values squared. That's why it's called least squares. And the usual sorts of things are defined according to, for statistical measurements, there is something called a chi-squared, which is really a reduced chi-squared. And then there's this thing this is the reduced chi-squared. Sometimes it's called goodness of fit, or maybe it should be called badness of fit. I don't know. Okay. So least squares. There's a heavy dose of mathematics in this particular part of the lecture. So just pay attention and don't take any notes. The lectures, I think, will be available on the web at some point or another. But basically, if you have a set of observations and some sort of a function that fits it, this is for linear least squares, like fitting straight lines through collections of points, then the best estimate of the values is found by minimizing this function, which is the weighted differences squared. And to do that, you have to take the derivatives of this function with respect to each of the parameters, and you create this, and then you set the derivatives to 0, because if you think about it, that's where the minimum difference between the observed and calculated data would be. And then you solve this expression for each of the parameters that are used to describe the model. That's fine if it's a linear problem. The problem with powder diffraction patterns and single crystal crystallography and all sorts of things like that is the functions are not linear. They're not even polynomials. They're much more complicated than that because they have transcendentals in them, namely things that do this. So you can't solve these things directly starting from nothing. You have to start with a model that gives you an initial set of parameters in order to be able to start it. And what you're actually solving in the least squares is for the shift between your original set of guesstimates and a better set of values. And then you say, okay, I now have a better set of values, and I do it again and repeat until the difference between the old set and the new set is minimized. So here's the math. Basically, you take that expression that I showed you earlier, expand it as a Taylor series, and toss out all the higher terms, and you wind up with this expression, namely that the calculated intensities are, for the new values, are the calculated intensities from the old values plus this derivative term, which depends on the shift in the parameters. That's the last piece and first piece in the Taylor expansion. So if you expand all this stuff out, substituting this thing back into that original equation for the minimization, you get an expression that looks like this. And notice that there is a derivative of the calculated function with respect to each of the parameters. And there's a product between one set and another set. So if you do this particular set of mathematics, on the next equation here, you get a set of equations. Yeah, is this thing lit? Sometimes it is. A set of, and there's not an analog pointer here. Nope, I don't see one. That's okay. I point with my fingers. So if you rearrange it, you would then wind up with a set of equations, one for each of the parameters. And so this can be used to describe basically a square matrix, which involves these terms here, which is the product of the derivatives of the points with each of the parameters. And so then, since you can do that, there is this matrix form, which is AX equals V. And what you're interested in are the X's, because that's the shifts in the parameters. So you have to solve this by inverting the A matrix here, which gives you a new matrix B multiplied by this vector, and that gives you the set of parameter shifts. You apply them to the old set and repeat. And you keep doing this until the thing has come to a minimum. All right. So the algorithms in various Rietveld refinement programs are different depending on which one it is. In the old GSAS and the old Rietveld program, it basically did it point by point. So I'm going to show you, if you watch this figure here, I can go over here, can't I? It processes it point by point, crossing through the pattern one by one with a whole series of nested do loops. Now, I'm writing GSAS-II in Python, and do loops or for loops are terrible things to use in Python because Python is a scripted language and it does every single line repeatedly over and over and over again. So the running times get really terrible. So you have to come up with a different algorithm. The different algorithm is shown here, where we compute the entire profile for a given reflection, all of its derivatives, and put them into this matrix, which is parameters by observations. It's a big matrix, because the number of observations here for, say, 11 VM can be 40 or 50,000 profile points. And the number of parameters this way can be a couple of hundred. So you can think of a really big matrix. This thing is called the Jacobian matrix. And you then do the reflections one at a time, working your way across the profile. And this, by the way, is very fast because there's no internal do loops. And the trick is that inside GSAS-II, these things are actually done with a little bit of Fortran, which is a very fast language. And you work your way all the way through, and I have to make sure I end on the last one there. And when you're finished with this matrix, you then multiply it by its transpose, that's that, and that gives you the so-called Hessian matrix, or the A matrix. And the matrix multiplication stuff inside Python is really, really very, very fast because, again, it's done by a library of routines which are actually written in Fortran. And I don't even know about them. I didn't write them. I don't have to worry about them. They just work. So anyway, that gives you the Hessian matrix. And you can then invert that and solve the problem. Okay. The method used inside GSAS-II is the Levenberg-Marquardt singular value decomposition algorithm. That sounds very complicated, but basically what this is an industrial strength dampening algorithm. And the way it works, and if I can get my little pointer to work here, is first of all, you compute the matrix. That's this step up here. This is slow. It has to go through that stuff that I showed on the previous slide. You normalize it, and the reason for doing the normalization is that when you look at this matrix here for a powder diffraction experiment in a Rietveld refinement, the terms inside this matrix can cover 16 or 17 orders of magnitude in some cases, which is really difficult for a computer to handle. So what we do is we simply normalize it by dividing each term by its corresponding square root of the diagonal. And that means the diagonal terms are all 1, and everything else on the sides is some small fraction of that. And that matrix is really easy to invert. You don't run into rounding errors. So the next step then is to compute the chi-squared, which is just simply the function to represent the powder pattern. You select a lambda, and you modify that matrix by this factor, 1 plus lambda. And what that does is puts a small increment on the diagonal. You invert the matrix, and I'll talk about this in a second, solve for delta p, and compute the new function. If the new function is more than the old function, that means it diverged. You then go back and increase the lambda by a factor of 10 and do it again. So you go back down here through this stuff. If, on the other hand, the new function is less than the old function, particularly after you've increased lambda, it then says, okay, that was a success. We apply the delta p to p, and you go back up here and recompute the matrix and start over. That's a new cycle of least squares. So the point of this business here is that this is basically the dampening. By making the diagonal of the matrix larger and larger and larger, it converts the thing to a diagonal least squares, which is an old-fashioned way of doing least squares refinements. And what that tends to do is to make the shifts smaller, and it's less likely for a parameter to, say, overrun and go too far. So then when you finally get to a point where the change in the chi-squared is small, say 1 part in 10,000 or something like that, you then quit and you're done. This whole thing is in about 40 lines of Python. And it's really robust. You don't have to have individual damping factors like with the old Rietveld programs. Full prof has them and things like that. So it's completely unnecessary. Okay. Singular value decomposition. If you want to read about this, go see mathematical recipes in section 2.9. And basically, what the problem is you want to solve for x by inverting a. Now, it turns out that for reasons which are not clear to me and not clear to the authors of mathematical recipes either, there is this little trick, is that you can replace a by the product of 3 matrices. And u and v are such that each one's inverse is the same as its transform. That's an interesting trick. U inverse is the same as U transpose, and V inverse is the same as V transpose. And W is a diagonal matrix. All of these things are the same size as the original A matrix. You get 3 50 by 50 matrices, something like that. You can then solve by doing this particular multiplication, which is V times the inverse of the W, remember it's a diagonal, and times U transpose. That winds up being A inverse. And so the trick is, what happens when W winds up being 0? Because it comes up with a 0 occasionally, and that's a singularity. Well, what you do is you cheat. You say, okay, I'm simply going to make 1 over W 0. So you replace an infinity with 0. And that basically takes that parameter out of the problem. And it does it away with all the ill-conditioned terms that you may have. Now, you have to have a sort of a tolerance, and W is typically somewhere around 10 to the minus 6 when this happens, to avoid parameters that are in near singularities. The problem with a near singularity in a refinement is if you allow it to go through, the associated parameter will be shifted over into this next province, to use a phrase in Canada. So if you do a refinement and you find some parameter has gone off, way off into the left field, that's what has happened, is that there's been a near singularity involving some other parameter, and it has gone very badly astray. Okay, this thing is inside Python, and I didn't have to write any of it. I simply had to go find it and call it. And the original stuff was written in Fortran probably 40 years ago. So this is old, very, very stable, very robust code. Okay. GSAS-II has 4 choices of algorithms for doing least squares, which are found in controls, and you're going to find out all about this when you try to use GSAS-II. And in controls, under refinement controls, is a choice of 4. Analytic Hessian, which is the thing I just described, and that's the default. Analytic Jacobian, which is similar but not different. There's no SVD associated with it, and it actually uses a built-in refinement package that's inside Python. And it always runs to some convergence someplace, so you never know how long it's going to run. There's a Hessian SVD, which doesn't have the Levenberg-Marquardt, and it might be better for single crystal data. There's also a numeric one and a numeric one, which uses numeric derivatives. In other words, it takes the model, steps one parameter, recalculates the function, and uses that to calculate that derivative. And it's terribly slow, but we use it for testing. So don't use this. Not unless you really, really, really need a cup of coffee or 2. Okay, a bit more on least squares. the error estimates are given by this sort of formalism, which means that the inverse matrix diagonal terms divided by the minimization function, chi-squared, gives you an estimate. You take the square root. Gives you an estimate of the error in that shift, whatever that parameter was. And if you dig around in the Rietveld refinement literature, somewhere back in the 1980s and maybe in 1990s, there were a number of papers that suggested, well, you should take these parameters and multiply by 5, the ESDs by 5, and these parameters you multiply by 2, and those you multiply by 10 in order to get our more reasonable estimates of the errors. Well, all of that is nonsense, because the problem is this, is that if there are systematic errors, i.e. inadequate models, which is always a problem in Rietveld refinement, the models are almost never perfect. There's always something left over in a powder pattern that you're unable to fit. And that will bias the parameters of the stuff you could fit because of the incomplete fitting. And so that's where all this comes from. Okay. Joel gave a nice overview of what this Rietveld model is. This is a very slightly different version of the model, which is probably has a little bit more in it because this is suitable also for neutron time of flight. And the reason is because the calculated intensity is then multiplied by the incident intensity from the source, which for neutron time of flight varies with time of flight. So it's different in different places, and it varies by a couple orders of magnitude, so it's not trivial. But all the terms that he talked about are here. We have the scale factors, the structure factors, reflection multiplicity, the various corrections, which include the Lorentz polarization, the absorption, texture, and all that stuff. I've lumped them all together. The peak shape function, which I'm going to talk about next, and a background function. So all of that goes into the Rietveld refinement model. It's a whole lot more interesting than single crystal crystallography, which only has structure factor. This is a whole lot more fun. Okay, profile functions. Joel showed you these. Basically, we have a Gaussian profile, and I hope his equation was the same as that one. Or very, very similar anyway. But generally the Gaussian profile comes from the convolution of the various contributions that you get when you build an instrument. There is slits, which are squares. There are, or rectangles if you like. There is the shape that comes off the monochromator, the shape in the source. And there's something called the central limit theorem, which says that if you take a whole lot of these different functions, all symmetric, convolute them together, the result will be a Gaussian, if you throw enough of them together. On the other hand, the sample broadening tends to be Lorentzian, and I'll explain in a few seconds why that is. And in brief, it's because the sample doesn't give you a single width contribution. There's a range of contributions depending on, say, particle sizes or the strain effects that makes that contribution Lorentzian rather than Gaussian. By the way, again, if you look around in the literature, you'll find back in the 70s and the 80s, lots of thoughts about, well, sample broadening is Gaussian and microstrain broadening is Lorentzian, et cetera, et cetera. This is, again, also nonsense because it's a misreading of the original literature by Warren. Now, if you convolute these two functions together, you get something called a void. It's a terrible thing to try to compute in a computer, so we cheat and use something called a pseudo-void, which is a linear combination of a Lorentzian plus a Gaussian with a mixing coefficient that puts the two together. And as Joel explained, Thomson, Cox, and Hastings described the mixing coefficient using a polynomial based on the based on these two widths, that makes the pseudo-void match the void over all combinations of shapes and sizes. Let's put it that way. On top of that, for constant wavelength experiments, namely laboratory diffractometers and also synchrotron diffractometers to some extent, is there's something called axial divergence. And I'll explain what that is in a few minutes. And the description of this was by Finger, Cox, and Jeffcoat back in the 1990s, if I remember correctly. One important point about GSAS and GSAS-II is that 2 theta is in centidegrees, not degrees, and the time of flight will be in microseconds. And that affects what the values, the coefficients are that you see in this. Most Rietveld programs use the same convention. Some of them use a different convention using degrees, and then the coefficients are corresponding a whole lot smaller. Okay, sample broadening. If you consider reciprocal space is the Fourier transform of real space, and if the real space is infinite in extent, and by the way, infinity in crystallography is around 10 microns, okay, small infinity, then the reciprocal space, what you see in reciprocal space will be an array of delta functions, infinitely sharp. On the other hand, if you reduce the size of the crystallites down to around a micron or under a micron, then the Fourier transform of those has a breadth. And the breadth of the reciprocal space spots is then the reciprocal of the size of the crystal. Okay? And you can represent that by saying that the width is a constant in reciprocal space. They're the same everywhere because you start with the same width of crystals in a sort of simplified way. And if you push your way through Bragg's law and a bunch of other stuff, you'll wind up eventually with the Scherer equation, which is given here. Yeah. Sometimes it's there. There we go, maybe. This is the S, which depends on the reciprocal of the particle size, that's P, and 1 over cosine theta. On the other hand, if the crystals have defects in them so that the unit cells are all slightly different sizes, then what you will see is that crystals with small unit cells will give you larger reciprocal lattice values, and crystals which have fewer defects, which are smaller because of the defects, will have the other way around. If it has the crystal's lattices are larger, then it will have you smaller reciprocal lattice points, and the smearing will be then proportional to the distance from the origin in reciprocal space, i.e. delta D over D is a constant. And again, if you push your way through all the mathematics and Bragg's law, you wind up with this expression where the broadening then depends on tan theta. And so this one is 1 over cosine, and this is tan theta. These two effects are easily separated in a 2 theta scan of reasonable length, like up around 100 degrees, something like that. Notice it depends on the angle. Well, that one depends on the wavelength. This one, the microstrain, does not depend on the wavelength. And the mu strain parameter is microstrain, so it's 10 to the minus 6 strain, dimensionless, otherwise a dimensionless pattern. Now, why do you get Lorentzians? Well, it's because, for example, of particle size, you don't have all the same size particles. There's a range of particle size. Small ones will tend to give you broad lines. Large ones will give you small, sharp lines. And when you add all these up, the resultant is a Lorentzian line shape. Okay? The same sort of argument can be made about microstrain, is that some crystals have a lot of microstrain, some of them have very little microstrain, and the superposition of these broadenings gives you a Lorentzian line shape. Okay. Occasionally you might ask the question, well, what is the balance between the microstrain broadening of Gaussian contribution and Lorentzian contribution? Well, GSAS-II allows you to do that by refining a mixing coefficient between this one's for size and that one's for microstrain. And they're simply mixing coefficients between the contribution of the Lorentzian term and the Gaussian term. And then these things are then put into the broadening terms, which I'll get to in a few minutes. And so what's done with that? So usually the case is that these two mixing coefficients are 1, namely it's all Lorentzian broadening, so that there's no Gaussian sample broadening and no Lorentzian instrument broadening. And okay, so let's get to the next point. In GSAS-II, we separate these two effects. Instrument broadening is in one place, sample broadening is in a completely different place. Now, do remember that both of those together will affect the line shape in the same way. So you can't refine the instrument broadening terms along with the sample broadening terms. That's a no-no, because that will yield a singular matrix, or really bad things happen. Okay? So here's a little page that shows you what the instrument parameters are, and they're all listed here for a constant wavelength machine. And the X and the Y, and there's a Z, which I'll tell you about in a few minutes, are all set to 0, whereas the Gaussian terms, U, V, and W, are non-zero, and this actually describes the instrument resolution. And you get a nice little curve plotted that shows you what the instrument resolution looks like. And what you should see is something that looks like a parabola for the Gaussian terms, regardless of what the instrument is. It could be an X-ray diffractometer, it could be a neutron diffractometer. They all have parabolic resolution curves. X-ray ones tend to flatten out at high angles, whereas neutron ones have a more distinct curvature to it. The minimum, by the way, in neutron diffraction more or less matches the monochromator angle on the diffractometer. On the other hand, the sample broadening is over here in a completely different place, which is characteristic of each phase in the sample, because each phase has different sample broadening, or can. And so it's over here underneath, say, phase silicon for a particular data set. So if you've got 5 powder patterns, each one of them could have different sample broadening effects, depending on how the experiment was done. And one of the things that's built into GSAS is the ability to plot out what the shape of the microstrain surface is, and also what the size is. And so that's given up here a choice of how you do the plot. That should have been microstrain, but that's okay. All right? All right. Neutron time of flight. And I'll spend a little bit of time on this, because even though this is at a synchrotron source, there are neutron time of flight sources around here, and you may be interested in using them, because, in fact, if you want to do neutron diffraction, you basically have to go to a neutron time of flight source, a spallation source, say SNS down in Tennessee, or you can go across the pond to ISIS in England, and you can do your neutron diffraction experiments there. Now, the thing that's different about it is that you have all that stuff that you had before, except it's now convoluted with this thing, which is a description of the pulse from the neutron source. You have a sharply rising exponential followed by a slowly decaying exponential. Now that's convoluted with the pseudo-void. And the resulting convolution is this horrible function here, which involves something called the error function. And then this thing over here is the exponential integral. That's what that one is. This guy is from the Gaussian component, and this guy is from the Lorentzian component. And so the peak shape function is this really messy expression. And these little terms, n, p, q, and so forth, are all function of the underlying profile coefficients that are associated with the time of flight. The alpha describes the rise on the exponential. The beta describes the decay on the exponential. Sigma is for the Gaussian. Gamma is for the Lorentzian. And so all these terms show up in the expression. Now, one thing that's important about the line shape is neutron time of flight peaks tend to be asymmetric. And it's a little bit counterintuitive, but the peak position is not on the fat side of the peak. It is on the sharp side of the peak. It is not at the peak top. It's offset this way. Okay? So if you try to fit this thing, sometimes there's some Rietveld programs which try to fit this thing with some horrible thing called a split Pearson 7 function, which has one Pearson 7 this way and another Pearson 7 that way, or a split Gaussian, stuff like that. Those things assume that the peak position is at the peak top, and that's actually a false position. Don't use those functions. Even if they're tempting, don't use them. Use the proper function for the description because it will give you the correct peak position. And why is this important? If you want accurate lattice parameters, use this function, basically. Okay. And the corresponding page is in GSAS-II, a little bit more complicated, but it's the same idea. We have instrument parameters on this side and sample parameters on that side. They're split. Okay, axial divergence. Basically, in order to get any kind of intensity out of a powder diffractometer, you have to have a slit that is of finite size. It has a height to it and a width. And ideally, the incident slit and the receiving slit are the same size. And the reason why you make them the same size is because one doesn't choke off the other. Okay? And this broadening is then because the slit, being a finite height, intercepts the Bragg at the Debye-Scherrer cone. First of all, it's sort of at one end, at the two ends, and progressively more as you scan further into the powder diffraction pattern. So the intensity rises up from some minimum value, rises up, has a little bit of a flat spot at the top, and then falls off abruptly once it passes on beyond the thing. This thing is then convoluted with the pseudo void. And the resulting profile function then has yet another term. And because of my little comments about how slits should match in a decently designed diffractometer, is that the original function actually depended on the sum of these two terms and their difference. The difference is assumed to be 0 in GSAS-II, and the sum then is the term that's refined. The values for the function are somewhere in the vicinity of 0.05 to 0.02 or 0.03 or something like that, depending on how high the slits are. How good is this function? Well, here is from a little bit of a protein powder diffraction pattern, taken at NSLS on a diffractometer where the slits were wide open in order to get the intensity up. And you can see the shapes of the peaks. There's this long rise and then a sharp drop off. And it basically nails it. Okay? Joel talked about this with respect to sample broadening, but this is a different one. This was a sample that had broadening, which was HKL-dependent, and it didn't fit the Warren-Averbach model at all for sample broadening. And so A model was developed, which is basically the idea is that the crystallites have some sort of elastic deformation because of defects. And it depended on what the elastic coefficients of this material are. Those are dictated by the symmetry of the material. And Peter Stevens and Nicole Popa basically came up with the same idea. Popa first and then Peter Stevens. Everybody calls it the Stevens model, but it really should be called the Popa-Stevens model, but never mind. And basically the idea is that you take the expression that's used to calculate the d-spacing, which is this, and say that there's some variance in the 6 coefficients. Normally, this one, by the way, is A star squared, and this one's B star squared, and so forth. But what we're interested in is the variance in these things. And so here's what the sample broadening is depends on the variance, which is the partial derivative of this with respect to each of the coefficients as a cross product between the two. So this thing's a matrix which is 6 by 6. But it has symmetry depending on what the crystal structure is. So the number of coefficients can be as little as 2 for cubic and 15 for triclinic. And you get shapes like that for the equistrained surface. In this particular case, this sodium parahydroxybenzoate, putting in the right model allowed us to find that hydrogen atom in a difference Fourier map, whereas you couldn't see it before with a bad fit. Okay, last topic, and that is how do you extract intensities from a powder diffraction pattern? Well, you have to have a fit first by a Rietveld method or by one of the other methods, which is the Lebye algorithm or by Pauli. For the Pauli method, it's fairly obvious. You simply make all the structure factors variables in the refinement. Now, this is fraught with problems because we have peaks that overlap. That means the 2 structure factors then become, you can't determine both of them. You have a singularity. So it has complex constraints and restraints put into the thing to avoid the situation of how do you deal with overlapped reflections. But nonetheless, it'll come up with a set of intensities. The other algorithm is by Armand Lebye, in which he simply said, okay, start somewhere with the calculated intensities. Doesn't matter what you start with. But once you've done that, you then get a new set by this extraction measure we'll talk about in a second. You use those as the observations for the next cycle, and then you repeat. And you get another set of observations, and you put those back in. And so these things are not refined. They're sort of cyclically estimated from the previous refinement. And the only thing that's actually refined is the background, peak shapes and peak positions, which is a small number of things. And it's simple, straightforward, and reasonably quick. Okay, so how do you do once you've got that done, how do you do the extraction, the intensity? Well, the way you do it is that you apportion the observed intensity according to the contributions from each of the terms in the calculated intensity. And so that gives you a value of extracted intensity to some particular 2 theta. You then go to the next 2 theta and do it again, and you then sum all the contributions that you find for each of the reflections. Apply all the corrections to back out what the structure factors are. And that gives you a new set of structure factors. And that's how it's done. And at that point, there was more. How am I on time?
2 minutes.
2 minutes till lunch. Okay, bear with me. I recommend that if you've never done a Rietveld refinement, I recommend that you do this one in GSAS-II first. It's fluoroapatite. Historically, this is probably the oldest X-ray Rietveld refinement still in use. because it's been done so often. It was the first example used in GSAS, and also, it's not the first one in GSAS, but it's the first X-ray one. The original data was collected in the 1970s by Ray Young and his associates, and was probably because he was interested in fluoride appetites. It's the principal component of teeth. And the way you do this is that you start off by putting in your initial starting model, and you do a default initial refinement, which is simply the scale factor in the background. You don't do anything else, because the scale is likely to be way off depending from what it ought to be. And you don't want to do a refinement on something for the model is as bad as that. So the first thing you do is the scale in the background. And here's the result. And what you should then look at is what is the shape of the difference curve, because that tells you what to do next. Okay, that's very important. And here's the kind of thing you should look for. If the peak is in the wrong place, then the resulting difference curve will look like a first derivative. It'll go up and then down and then back 0, because the peaks are in the wrong place. Now, this is because, say, a lattice parameter is wrong, or a sample displacement is wrong, or something like that, which affects the positions of the peaks. The second thing is, I'll start over here, is if there's something wrong with the crystal structure itself, then the resulting difference curve is simply going to look like the diffraction peaks, but they could be plus or they could be minus. But the shapes of the difference curve, say here, is going to be the same as the shape of the original diffraction pattern, just scaled up and down. Okay, the other problem is going to be if I have here a size too large, but it also could be microstrain too small, which is actually a more common situation, is that the calculated peaks are too sharp relative to the observed ones. That's very typically what happens. And so what you then see, and it's a little hard to see this, but the difference curve will go up and then down and then back up again and then back, because there's alpha 1, alpha 2. But the point is, it looks like a second derivative. So it goes up and then down and up and then down like that. That's a second derivative curve. So, but you can tell because the peak shapes are wrong. They're usually too skinny relative to the observed data. So this is what you should be looking for, is first derivative, wrong position, second derivative, wrong shape, zero derivative, if you like, something wrong with the structure, or something else that corrects the intensity of the peaks. Okay, and then, so we looked at this particular difference curve, and the most characteristic thing about it is that you had this up, down business that looked like a second derivative because the calculated peaks were too sharp. In this particular case, it's because the microstrain was too small. So you refine logically the microstrain parameter, and it seems to be a little bit of offset because what you actually see is some linear combination of those three things I described. And then so you throw in the lattice parameters to get the peak positions right. And the thing is, that's most important is this. Every sample is different. You never know what you're going to face until you actually start doing it. There's no recipe, except look at the peak shape, look at the difference curve. Okay, so you put that in, and it immediately improved. And all that's left is intensity errors. Don't be surprised here because you have alpha 1 and alpha 2. So both of them are off by about the same proportion. So the next thing you do is refine the coordinates and the temperature factors, and you're done. This stuff that's left over is what I talked about earlier, is that in a Rietveld refinement, there's always something left over because the models are not perfect. They're imperfect. They don't cover absolutely everything. And So anyway, there's the result, and you can draw a nice picture of the structure. What's next? A useful plot when you're done is to look at the covariance matrix. And this gives you the correlation between pairs of parameters in the least squares. And it's represented by green squares are where the covariance is positive. Red squares are where the covariance is negative. In other words, this one parameter goes up, the other one goes down. Yellow is it's around 0. Mellow yellow, you know. The green diagonal simply represents the self terms, and what's actually in there is going to be the value and the ESD. The thing to beware of is if you see white bands or not a numbered kind of values reported, that's because there are singularities in your refinement. Okay, a few final words. A Rietveld refinement is never perfected. It's merely abandoned. And that was from Peter Stevens. Sue Keeson put in this line about it's one of the few things where the more you do it, the less you understand. And there is a certain truth to that. And what I said is, you're done when you run out of parameters. And some books that were so predate what Joel gave you. But the nice thing about this one is that it costs you about $10, or maybe it's 20, from the Mineralogical Society of America. And I think there's an updated version since that 1989 reference. And I think at that, I can say thank you. By the way, I started this game in 1971. That's a little while ago.
Questions for the book, please?
Questions? Anybody? Everybody understand? Oh, go ahead. And you'll have to shout because I'm deaf.
So when we are with performing a refinement on any crystal structure, sometimes we are getting positive or negative values for UVW. So what is that?
Is the curve parabolic?
Mm-hmm.
Okay, you're fine then.
So those values like U, V, and W, those are must be like.
Usually V is negative. That's in the classic neutron pattern diffractometer. V will be negative, and the curve will look something like this. For X-ray diffractometers, the curve tends to be sort of steep at low angles and then sort of flatten out, and all kinds of things can happen to the coefficients. But yeah, it doesn't matter. It doesn't matter just as long as that curve doesn't go below 0. If it goes below 0, you need to fix it and get it back up so it's positive.
So if we can get the V positive, then that's.
And by the way, you shouldn't be refining these things because they're instrument parameters. So they should be only refined from a standard. Lanthanum hexaboride, silicon, alumina, something which has a known sample broadening. And by the way, in GSAS-II, when you do those things, you have to put the appropriate sample broadening coefficients in as known quantities. Then the UVW will come out right. Okay? That's just something that people tend to forget. Because the default value for the microstrain is 1,000, which is a common value. But lanthanum hexaboride, the right value is more like 330, something like that. And the same thing with the particles, the crystallite size. The default is 1 micron. Lanthanum hexaboride, I think it's somewhere around 1 micron, if I remember right. Silicon, I'm not sure what it is, but you have to look at Jim Klein's certificate to see if he says what the sizes ought to be, and use those numbers. Okay?
Okay. I have a question. So, is it so using this refinement, can I do only one data at a time, or is there a process where I
GSAS allows you to do multiple data sets.
Okay, so if I have like an in situ data where I have like 100 set of data together, so can I put everything together at a time?
Assuming both of them have the same phases in them, yeah.
No, what if the phase changes over time because it's an in situ data?
If you have a sequence of data sets, say you're doing a temperature study, then what you're allowed to do in GSAS-II is to refine them in sequence. And then at the end, you get this table of values, which depends on temperature.
Okay.
And then you can plot them out and look at them. Very useful, or can be. Anything else? Yep.
Okay, so I have a question. Can we use multiple order patterns to find against them at the same time?
Yes.
So let's say if I accumulate more intensity at high angle region,
Well, you should use an entire powder pattern. Okay.
Yeah.
Because things like the particle size and the microstrain, the crystalline size and the microstrain, depend on the angle, for example. And so if you don't use the full data sets, you can't really get at those values very readily. It's much more useful if you're doing things like you have an X-ray pattern and a neutron pattern, and you're interested in the changes in the atom contrast in a mixture, for example. Another case is that if you do experiments at a synchrotron at different energies around a resonance, the resonance changes the scattering factor. And so you can distinguish between adjacent elements by changing the scattering factor of one of them by tuning in on the edge. But be careful. The first talk showed what happens to the absorption coefficient above the edge at higher energy. It's got all these wiggles in it. Don't collect data there. That'd be a bad place to collect data. One is you're going to have a whole lot of fluorescence background. The second is you have no idea what the absorption coefficient is because it depends on the detail of that curve. And I noticed that those fluctuations were like 20% of the absorption, 10 to 20%. So that's a lot. So yeah. But if you see on the other side of the edge, then you're okay because the absorption is low, the resonant effect is large, and you've shifted the form factor by a lot. Okay. Joel mentioned, I think, that there's this absorb routine that you can use to calculate what the absorption coefficient is based on your composition. That's actually built into GSAS-II. And there's another one that's built in, which is called F prime, which computes what the change in the resonant term F prime is according to the wavelength. And you use that to design experiments selecting the appropriate wavelength for resonant effects. Okay? Anything else?
Yeah.
Oh, yeah, go ahead.
I was interested in the microstrain graph picture that you showed. It's like what kind of information I can get? Is like this is the strain in the unit cell, or is the strain in the, because the axis, like it's better to use the axis in the normalized, or if I want to compare with other samples, or
That's a really interesting question because we think that there's a connection between the elastic strain coefficients in the material and those figures, but we don't know what the connection actually is because we have no idea what the stress is. Okay.
Because my question is, I am studying residual stresses. I want to know if I can use like this matrix to convert in a stress.
I have no idea. And the reason why I have no idea is because we generally, if you've got a crystalline sample which shows this, you have no idea what the stresses are on those individual crystals that give you that distortion. And remember what I said is that defects in the material will also give you those distortions. You have no idea what the internal stresses are from that. But the shape of those things is very, very suggestive of the...
I imagine that figure is made from the reciprocal space, or no? It's in the that big image is in a real space or in a reciprocal space?
I have to think about that one. It's dimensionless because it's strain. Okay, so it's a real space thing. Okay, but it's dimensionless. It's the microstrain, 10 to the minus 6 strain, and those are equal strain surfaces that are being plotted. Okay. There are some papers that by various people in Europe where they have tried to understand what the actual microstrains are and the effects of twinning and defects, faulting on what that is, and it's really complicated because it depends on what the faults are. Stacking faults, shear faults, and things of that sort. Okay? Yeah.
I tried to do this map strain, and I got like a spherical distribution, so that with a different magnitudes, and I want to know what does it mean,
Yeah, right. Yeah. No. Well, there probably is something to it, but it's hard to know exactly what it is because you have to know much more about the internals of the material in order to understand it. Okay? Yes.
What about if there are other questions, we catch up with him during the workshop. We have 3 days, and it's lunchtime now, and we have to be back in 1 hour. Okay? Thank you.